Okay, so let's look at how derivatives manifest themselves in the physical world in one way, at least today, and then we'll start to mess with that with a little bit of a motion activity another day. Okay, and then I also wanted to prove that one rule to you. Okay, so I'll prove that too.
Power one?
Okay, so first, what is distance? What's the way you can express distance you've known for a very, very long time? Distance is rate times time. Yeah? Okay, so if you just dissect that a little bit and then bring in the idea of a derivative, you get something really nice. Okay? So another way to say rate is velocity. That's really just another way to say the same thing. Okay? And so then we have velocity. Now I'm going to write it as a function of time because we're working with functions in calculus, right? So I'm going to say velocity equals, if you move this around, what do you get? Velocity equals what?
Time divided by distance. Yeah.
Distance
divided by
Distance
velocity.
divided by time, right? If you divide time to the other
What
side.
are we going to get velocity?
I don't know. That's all right. So velocity is distance over time. It's super simple, right? But now in calculus, we have a way to represent distance. So if we have like a distance graph, we can call that change in position. And then time is just some change in time. Because when you say a time, you're thinking like from some starting spot to some ending spot. And when you think of a distance, you're thinking from some starting spot to some ending spot, y value wise. You guys know what I'm saying? So when I say S there, S is the way that we're going to talk about position. Okay, so S means position here. So this is, if you think about it in words, I guess I'll write it in words in a different color. This right here is the average velocity over some time interval. So maybe time t1 to time t2. Some time interval, that's the average velocity, okay? Now in calculus, we took average things like secant line, the slope of a secant line, that's like the average between two parts on a function. We also call that the average rate of change. And we did what with it? We shrunk it down with a limit and made it not average, but instantaneous. So I think the idea here then is apply that to the velocity. So velocity is this. That's pretty simple. Could have done that since we were pretty young. And apply a limit. So take a limit as your time interval shrinks down to nothing so that you get to an instant. Think about the position function of t plus a little bit of change minus s. So there's the y values on your position function. What should I put on the bottom of that thing? T. Change in the x values is now change in the t values, right? That's what velocity is. If you want to change from average velocity to instantaneous velocity, all you have to do is put that limit in front of it, and now you know the instantaneous velocity at any point in time of any curve that you can describe. So if you have a curve, some curve out there in space, and we'll be generating some curves with our bodies and some bouncy balls and some different things. Maybe I'll get a pendulum at some point this semester. I don't have one yet, but I'll find one. We'll be generating position curves. So this on this axis, maybe it's like a height, or maybe it's like how far it is. That's a position, right? It could be this way, it could be up and down. Any of those things are positions against time. Now, instead of just knowing the average change in position, which gives us the average speed from like here to here, now we're going to be able to go and look at things like right there, at that point in time, what's the speed that this object is traveling? So it looks, the speed that it's traveling is the slope of that tangent line. The speed that it's traveling is the velocity. So the velocity is, in other words, s prime of t. Velocity is the derivative of position. If you have any curve that describes position, whether it's how far away like horizontally or how far away vertically, and you take its derivative, you've got velocity. Isn't that like crazy? It's so nice though. It's so, if you want to know how fast stuff is traveling, and oh, velocity, does it just say how fast stuff is going? It's a vector quantity. It includes how fast something's going, but it also tells you which direction, like positive or negative, and we'll see that when we use the motion detector and like mess around with it, okay? So, if you're taking physics or you've ever learned anything in a science class, there's this other thing with position and velocity. What's the other thing that's related to those?
Acceleration.
Acceleration. So does anybody care to guess how you might get acceleration?
You take that minus, what is it, 0?
Acceleration, if you, I hope you guys at least kind of remember, is change in what over change in what?
Velocity
Over time. So if you apply the limit argument, you can stick a limit in front of it just like that. Then another name for acceleration is now what?
So you take the derivative.
You can take the derivative of this again, because you're going to have velocities here, right? So you can take the derivative of what you had here again, or you can just start with where you started from at the beginning, position. And if you take the derivative twice, that's called s double prime of t. That is acceleration. So anytime you have anything that you can describe with how far away it is and stuff, now you know how fast it's going anywhere at any point in time in the future. Now you know how fast it's accelerating at any point in time, anyway, any time in the future. So it's like super powerful. That's not the only thing derivative does, but it's a big thing. Because now calculus basically provided us a way to understand all motion, anything that moves in the universe. There you go. If you take another derivative, like a third derivative or a fourth derivative, those also have applications. They're just not as commonly used. So like whiplash, I think whiplash is the fourth derivative. And there's crazy names for them too. You guys should look them up on Google. I think that there's snap, crackle, and pop. Snap, crackle, and pop actually mean things. They're derivatives of position. They're just further down the derivative line. They just aren't very commonly used, you know, they don't matter very much, but pretty interesting. Yeah, so those are motions too. Okay, so where would you need something like this? Let me do a couple simple examples. Let's do some simple stuff. Okay, so let's say we have a position function.
These are examples.
Yeah. So let's just say someone comes along and says that's the position. If you take physics, you'll start to learn why that might be a position of something that's free falling. Like something that's in free fall has a function that looks like that a lot of the time. So a lot of the time, something that's in free fall, well, all the time, something that's falling always has this. That's the equation of anything that's falling out there on Earth. G is the acceleration of gravity on Earth. If you go to another planet, of course, it's different. So in meters per second, what's G?
9.8.
9.8 meters per second is usually directed downwards. This one doesn't have it as 9.8. It's not in meters in this problem. Can you guys guess what units this is in? I think it's 32 feet per second squared. Well, sometimes we're English, you know. That's what G's value is in feet per second squared. It's not very kosher for the rest of the world, but okay. What do you guys think these mean? People who've had physics should be able to help me more.
Original velocity.
Original or initial velocity.
Original position.
Original position. So anytime you have a subscript like that, it just means at the beginning, initially, originally. Yep. So So that's how the equation of something in free fall. We can talk about that for a while, but here's a problem. So there's G, that's just gravity. This guy's moving how fast at the beginning?
Speed
16 feet per second. And how high was it originally? 32 feet. So what I said this was is I said this is the position of a diver who jumps from a board that's like a diving board. It's 32 feet high, and at the very beginning, like after they jump and use their legs, the initial velocity is that much. Okay?
I can dive now.
So my question is A, when does this diver hit the water? So that's what I want to know first. The other thing is, what is the diver's velocity at a couple spots? So let's say 1 second and 2 seconds into the jump. How fast is she going right then? Not average, right then. You can't do that without calculus, so I couldn't have asked you that in physics. Unless it's a calculus-based physics class. Yep. So let's do part A first. When does she hit the water? Do I need velocity for that? No, that's talking about her position, right? In fact, if she hits the water, what's her position defined as?
0.
0, so I should put 0 where?
On that side. To the left.
0 for S. And solve. So can you guys solve that for me real quick? I'd divide through by 16. I'd divide through by negative 16. Yeah, if you divide through, it makes it so much easier. And you say, okay, gonna factor that guy. Minus 2 plus 1, so the times that she's at 0 are those 2 times. Do both of those make sense physically? Negative 1 means back in time 1 second. She was on the diving board back in time 1 second, so that doesn't make sense. So I think that this one is an extraneous solution. Doesn't make any physical sense. It's like a byproduct. We should, of course, put seconds. Make sure we have our units. So that's that one. How do I do this one? What's her velocity after that?
I would start by taking the derivative.
Start by taking the derivative. So v of t we just said is s prime of t. So we take the derivative, which is what? Help me out.
Negative 32t plus 16. That's
Plus 0.
it.
Yeah? We okay with that? Anybody have a question? Just for shortcuts? T to the 1 technically, right?
Well, yeah.
Wait, what did you do? Oh, you pulled it down and
If
then.
you really want to think
Just
about
using
it,
my power rule, which we're going to prove in a
when
second.
you have
But
t
you-
to
so
the
you just get
first,
rid
you
of-
pull a 1 down, and then it's t to the 0, whatever.
You just get rid of the 32?
Why? Remember you're taking the derivative of each term separately?
So the constant is 0, or the
Derivative of a
so
constant is
it's
0.
So does the t go away on the second part?
Yeah.
What do you guys think?
If you
you
think
put
about
on
it,
the
you
one.
can use the
Because
power
you
rule
go
again.
n minus 1, right?
You can really use the power rule again. I like Jake. He's saying you can bring that down and that's just
Right.
16 times 1, and t to the 0 is
Oh, it's like okay.
1.
Yeah.
So, of course, you could also think about it with the slope, right? If you're just thinking a line, what's its tangent line everywhere? The slope of the line, which is 16. Yeah, there's all kinds of ways to think about it. Anyway, you've got that. So now it's really easy to answer this question. You just say the velocity at 1 second is?
Negative 16?
Feet per second.
Oh, yes.
I know.
Thinking physics.
I want to put everything in meters now.
It's good.
It's better that way.
And that makes sense. Why does it make sense that her velocity is negative?
Because
She's falling. She's going
Going
down.
down, right? That makes sense. Her velocity at 2 seconds. What do you guys think? Is it going to be more or less?
More. You're accelerating.
Remember, we already did this part. So at 2 seconds, it's going to be more because you're accelerating from gravity, yeah.
But I mean, like you.
Oh, she hit the water.
But she
Right,
hits the
like-
water there. So that is another way of saying how fast she's going when she hits the water. That's why I asked that question. She's going pretty fast. If the diving board was a little bit higher, do you think she'd be going an equal amount faster or how much faster? I think it'd be a lot faster, like 3 seconds. Think about like if this was higher. So let's pretend the water was lower and you put t equals 3. How fast is she going now? Do it.
Critical point,
Yes.
are they doing that with the fractional absolute value?
When times 3.
Anytime you have an inequality,
She fold?
I'm not sure how it
Technically,
works.
she's going.
Is the diving board
It's positive or
higher?
negative, it should be rather considered equals like
In my mind.
So what kind of function is in the inequality?
Thought everything's
Water was
needed
lower.
for
So it's absolute value of this quadratic.
Well, technically, you're still falling down with the water because you're going down.
Like
Yeah, but the you don't. Then you have to actually back again.
So, but
Water is
like
water.
where you had it in the video, you were saying, for sure for the fractional
And they're
problems.
both.
Yeah, there's just my two.
Okay.
I just wanted to check that they could do a critical point check because they can never pass
No, we're
college
like, we do
algebra.
what we want.
Right.
A in college algebra without being able to do that. They should not pass. If I was teaching college algebra and they couldn't do a critical point chart, they would not pass the class.
The following students to student
So,
services
On, because I was gonna have them do them for that fractional absolute value problems as well.
and Michael Harris.
Actually,
Hey,
was
did
just
you see
higher.
S3?
Well, don't hit there, please. You might miss.
Oh, I did it.
Have to go back to the original absolute value, right? They can't go to the one that
Bring
they.
out those cards in.
Can you ask me a second? Because I've got to keep going. I'm sorry. I'll
I know, it's hard
work
to
it out.
describe.
No, I gotta finish this.
Do you see anything about the?
Can you wait a few minutes, or?
Super rare Pikachu
Okay,
card?
let's do this last thing, guys. So how much faster was she going? Can you tell me? At the water, she was going 48 feet per second down. How fast after 3 seconds?
Negative 80 meters per second.
Negative 72, 80, what?
80.
80? Ooh, I think that's gonna hurt. So thank goodness she didn't get to go for that extra second. Okay, so I promised you that I would prove, oh, I don't even need to. So the derivative of x to the n. We know that that is what from yesterday, because I just told it to you and we kind of guessed it from a few examples.
Is to the n x to the n minus 1.
Okay, here's the proof.
Is it long?
Yeah.
Okay.
Okay, we're going to go back to the limit definition, because that's where all calculus comes from. So I'm going to say the limit as h approaches 0, f of x plus h, well, let's write it down, I guess. F of x plus h minus f of x over h. So now we're going to plug in, right? So we say f of x plus h is what? X plus h to the n power, yeah? Minus x to the n power over h, yeah? But very quickly you're going to see this does something unusual when you're trying to do it. So yours, you were like, oh, just multiply by the conjugate, make a common denominator, do something fairly simple, and you just get stuff to drop out. But this doesn't work like that. Why? What's the only thing you can do right here?
Expand.
If it was x cubed, you expanded it, right? Remember how we used Pascal's triangle? Well, this doesn't have a specific value.
It's got like a dot dot.
Does that mean you're just lost? You don't know how far to go, right? So Jake said, why don't you just write it with a dot, 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 and kind of see what happens, see how things go. And that's the idea. So you go back to Pascal's triangle. So I'm just going to write the first term.
Corey Howard, Anthony Hurney, Alex Lopez, Austin Maddox, Isaiah Poe, Andrew Robertson, Derek Samuelson, and Ryan Lord to student services.
Yes.
Okay, so
Even yet.
the first thing is x to whatever that power is, right? So we have x to the n.
Cyborg attack.
And are there any h's on that first one?
No.
No. So then we have the next term. The next term will be x to n minus 1, whatever that was, right?
Right.
And there's going to be how many h's on that? One h.
At least one.
And there's also going to be something sneaky hiding in right here, right? Isn't there going to be some number from Pascal's triangle? So I'm going to call it Pascal number 1. Okay, and we'll come back to that. And then you have to keep going for you don't know how long. So let's write out a couple more and we'll use Jake's ... So we go, okay, then there's another number from Pascal's triangle, but it depends on where you're at specifically. So I'm just going to call it Pascal number 2. And it's times x to what power? N minus 2. And how many h's? 2 of them squared, right? Okay, then we don't know how long this process is going to continue, so let's say plus ... plus. Let's write out a couple on this side. So we're going to have some Pascal number again. We don't know which one it is. We'll call it Pascal number 3.
To student services, Reese Bennett, Kelvin Griffith, Nick Hastings.
What else is going to go on this? Let's write out 2
Laura
more.
Miller,
Okay?
Eddie Phelps, and Mandy Wyant to student services.
X.
Okay. So this is the very last one. Does it get an x? No. Does it get an h?
Yes.
Yes. How many?
All of them.
All of them. Okay, this one. How many h's does it get?
N minus 1.
Okay. How many x's does it get?
X.
Just 1. So I chose to write out that many. The idea is we're trying to find the pattern and see if we can make a difference, yeah?
Why is there a Pascal before the last h but not before the first x?
I guess that at the what are those the first I guess there could have been one here too is just ones. So I guess this is just a 1. So we can probably just say that. Good point, Adam. Very nice. Okay, and then what else do we have? So that's this. What else is left still?
You have a minus x to the
Minus x to the n.
so those go away.
All over h. And we say, hey, well, at least something went away, right? These go away, or x to the n's. And does somebody see something else that might happen?
You can factor out an h.
You can definitely. All those other terms have an h in them, don't they? All these terms up here. So you can pull it out. I have it in blue, so I'll keep it in blue. Let's see what's left then. We've got
X to the n minus 1.
not just x to the n minus 1, look in red.
Pascal number 1.
Pascal. Yeah, you could. That's fine. Pascal number 1. But there's something there, right? And we have an x to the n minus 1. And then plus here we've got
Pascal number 2.
Pascal number 2. And what else?
X to the n minus 2h.
X to the n minus 2 and 1h. And then plus ... plus. Try to maintain this. Yeah, you could definitely call that stuff, Adam. You just got to realize there's something there. Yeah? And then you've got what on that one?
Pascal.
You've got an
number
x.
3, x to and h to the n minus 1.
You factored out an h.
Oh,
h
sorry,
to the...
h.
Is that right?
Minus 2.
I think it's minus 2. If you're unsure, multiply these back together. What's h times h to the n minus 2? That's h to the 1 plus n minus 2 is h to the n minus 1. I've got it. You should be able to do that. That's like super important math right there. Okay? And then do we have anything else left? That was this one. We took an h out of that last one, so plus
H to the n minus 1.
h to the n minus 1. We had it all over h,
Those go away.
gone. Oh, and now I'm just going to not even write it. I'm going to use the
Corey
limit.
Howlett, Anthony Purdy, William Houghton,
So everything
and
except
Eddie
x
Phelps to
minus
Student Services.
1. And your Pascal's number 1.
Okay, have a look at this. Everything with h in it goes to 0 now, right? So what's left that has h? That doesn't, so that's still there. This had an h, it's gone, went to 0 with the limit. This next one's gone, 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 gone. This has an h, gone. This has an h, gone. Everything else is gone except this part. Does that look familiar?
It's bracing.
So Pascal number 1 must for some reason be n. Well, if you do Pascal the long way, all those coefficients, 1, 2, 3, all those things are choose. They look like this. The first one is n choose 1, that's Pascal number 1. The next one is n choose 2, n choose 3, dot, 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 and you just keep going. If you remember, another way to write choose is with the C, n choose 1. And how does that go? Can somebody help me? And choose 1. How do I write that out longhand? From ages ago. Has what in it? Factorials. It has factorials in it. I think we go n factorial. Then we go n minus, you have an n minus 1 factorial. That's permutation. And then you have to use that right here too. 1 factorial. What's 1 factorial? 1. So this is. And how do you simplify that? That doesn't look like n to me.
But it is.
But it is. Why?
Because it's just starting off. It's like if you had number 5, for instance, you have 5 times 4 times 3 times 2 times 1. So at the bottom you have 4 times 3 times 2 times 1. So you're just left with 5.
Yes. So the way you rewrite factorials is you can write n factorial as n times n minus 1 factorial, can you not? 5 factorial is also 5 times 4 factorial. Gone. N.
Wait, say that again?
The reason that's true, you can rewrite factorials like that. 5 factorial is also 5 times 4 factorial. That's why you can rewrite that dot part. Okay? So that was a little bit heavier duty, wasn't it? So I'm not going to prove everything that we learned this year, but I'm going to prove a few things here and there. So that's a proof. No questions about it anymore.